There are roughly 2 trillion galaxies scattered across 93 billion light-years of space. It feels boundless, an open invitation to explore forever. But hidden inside that gentle assumption is a devastating truth. Most of what you see through a telescope is already unreachable. Not far away, not merely difficult to visit. Unreachable, forever, no matter what technology we build. Under our best cosmological model, expanding space-time has drawn a permanent line around what humanity could ever touch, and that line sits far closer than the edge of what your eyes can see. In this journey, we will separate seeing from reaching, calculate the true frontier of our species, and discover the largest domain any human civilization could ever realistically call home. Prepare yourselves for a boundary you cannot cross. If you find yourself genuinely curious about the real edges of our future in space, consider hitting the like button and subscribing so more stories like this can find you. Also, before we begin, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, get yourself comfortable. Let's begin. Step outside on a clear, moonless night and let your eyes adjust to the darkness. Look up. Even in a modest sky, far from the harshest city lights, you can see a few thousand individual stars. Every one of them belongs to our own galaxy, the Milky Way, and every one of them lies within a few thousand light-years of Earth. That already feels vast. 1,000 light-years is a distance so extreme that a beam of light, travelling at roughly 186,000 miles every second, needs a full millennium to cross it. Yet those visible stars are barely the edge of our own front porch. They are not even the beginning of what the universe truly contains. Point a modest telescope upward, and the count leaps by orders of magnitude. Point the Hubble Space Telescope at a patch of sky the size of a grain of rice held at arm's length, and thousands of galaxies appear where the naked eye saw only empty darkness. Now aim the James Webb Space Telescope at the very same postage stamp region, and the numbers climb again, revealing faint smudges that turn out to be entire galaxies as they existed more than 13 billion years ago, when the cosmos was still fresh and hot, and only a few 100 million years past the Big Bang itself. Extrapolate this exercise across the entire sky, in every direction, and modern astronomers arrive at a number that is genuinely difficult to hold in one's mind. The observable universe contains roughly 2 trillion galaxies, 2 million. Each of those galaxies contains, on average, somewhere between 100 billion and a few 100 billion stars. Multiply through, and the visible cosmos holds more stars than there are grains of sand on every beach and every desert on Earth combined. It holds more stars than there are cells in every human body that has ever lived. This is the empire we can see. This is what your telescope invites you to imagine walking through. And under that invitation lies the most seductive assumption in all of astronomy, that if you can see it, one day you might reach it. That assumption is wrong. It is not merely wrong because our engines are slow, or because human lives are short. It is wrong at a level that no engineering breakthrough could ever repair. Under the best cosmological model we have, most of the 2 trillion galaxies you can see tonight are already, right now, permanently beyond the reach of anything humanity could ever launch. Not just beyond the reach of chemical rockets, not just beyond the reach of fusion drives, antimatter engines, or hypothetical light sails. Beyond the reach of light itself, beyond the reach of a laser fired today with unlimited power and perfect aim. Beyond the reach of every possible signal, probe, mission, or civilization our species could ever produce. That claim is difficult to accept the first time you hear it, and it should be. So, let us build the case slowly, carefully, and honestly, because the truth of humanity's ultimate frontier depends on understanding a distinction that most people never encounter. The distinction between seeing something and being able to reach it. Start with what the word observable actually means. When astronomers speak of the observable universe, they do not mean a sphere with a wall around it. They mean the region of space from which light has had time to travel to Earth since the beginning of the cosmos. Roughly 13.8 billion years ago, light travels at a finite speed. The universe is a finite age, so any light source too far away, at the moment the universe began, will not yet have delivered a single photon to our eyes. The boundary between those two categories, sources whose light has arrived and sources whose light has not, forms an imaginary sphere centered on Earth. That sphere is what we call the particle horizon, and its radius is roughly 46.5 billion light-years. That number confuses people the first time they hear it. If the universe is only about 13.8 billion years old, and nothing moves faster than light, how can we possibly see things that are currently 46.5 billion light-years away? Should not the answer be 13.8 billion light-years, and no more? The answer would indeed be 13.8 billion light-years if space itself were not expanding. But space is expanding. The distance between distant galaxies is not fixed. It grows everywhere, all at once, in a smooth stretching of the underlying geometry. A photon emitted 12 billion years ago from a galaxy that was, at that moment, only a few billion light-years away, travelled for 12 billion years. But during those 12 billion years, the space between us and the source stretched. By the time the photon arrived at Earth, the source galaxy had been carried much further away. Its present distance, what astronomers call its proper distance, can be tens of billions of light-years, even though the light itself only travelled 12 billion years to reach us. The particle horizon is the present-day distance to the furthest sources whose ancient light has reached us. The most distant of those sources, when their light first left them, were much closer. Expansion has since carried them outward, to positions that lie far beyond a naive 13.8 billion light-year sphere. This is your first hint that cosmic distance is not one number. It is at least three distinct concepts that mean very different things. The first is co-moving distance, which asks where a galaxy sits in the underlying grid of space, corrected for expansion. It is the distance you would measure if you could freeze the expansion of the universe and stretch a cosmic tape measure between yourself and your target. The second is proper distance, which is the actual present-day separation between you and that galaxy right now, this instant, at this snapshot of cosmic time. For very distant objects, proper distance and comoving distance are close cousins. The third is light travel distance, which is simply the number of years the arriving light spent in flight. These three numbers can differ from one another by tens of billions of light-years for the same galaxy, and confusing them is the single most common mistake people make when trying to reason about what humanity could reach. So when we say the observable universe has a radius of 46.5 billion light-years, we are talking about proper distance right now to the furthest sources whose light we can currently detect. That light itself only travelled about 13.8 billion years. And when that light was emitted, those same source galaxies were much closer to our position, less than 50 million light-years away in some cases. So close that the very concept of our position is strange, because Earth did not yet exist. Once you internalize this, a strange and beautiful realization follows. Everything you see in the night sky is a message from the past. The star, Sirius, only about 8.5 light-years away, appears to you as it was 8.5 years ago. The Andromeda galaxy appears to you as it was 2.5 million years ago. The most distant galaxies James Webb has captured appear as they were more than 13 billion years ago, when they were young, small, and chaotic. You are not looking at the universe as it is. You are looking at a mosaic of moments, each one arriving from a different depth in time. There is no such thing as a snapshot of the universe as it exists right now. The finite speed of light forbids it. To feel the weight of this, let us pick one specific galaxy out of the 2 trillion and hold it in our attention for a moment. Consider a galaxy roughly 10 billion light-years away, in proper distance, an ordinary spiral not unlike our own Milky Way, sitting somewhere in a random direction in the deep field. Its light, arriving at Earth tonight, left that galaxy when the universe was only about 6 billion years old, when Earth had not yet formed, when the atoms that would eventually become your body were still scattered across countless generations of dying stars. We can study that ancient light. We can measure its chemistry, its rate of star formation, the shape of its spiral arms as they existed billions of years before life on Earth began. We know an enormous amount about that specific galaxy. In some ways, we know it more intimately than we know most places in our own solar system. And yet, at this very moment, As we look at that galaxy and admire what it once was, we can also compute something about its future. If we sent a signal toward it tonight, that signal would never arrive. Not because our transmitter is not powerful enough, not because our aim is imperfect, because the geometry of the universe forbids it. That galaxy is currently receding from us at a rate that outstrips light itself, and expansion will only accelerate the shortfall. Any message we could ever send it will fall behind and stay behind forever. We know its face. We have measured its chemistry. We understand its history. But its future is not a future we can participate in, ever, under any circumstances, using any technology that could ever be built. That is what it means to see something without being able to reach it. That is the strange, quiet loneliness that hides inside every deep field image. This alone is unsettling. But it is not the boundary that matters most for our story. The particle horizon tells you how far you can currently see. It does not tell you how far you could currently reach, and those are almost never the same number. To understand why, imagine a simple thought experiment. You point a laser at a galaxy you can see right at this moment, sitting perhaps 30 billion light years away in proper distance. You fire the laser. The photon leaves Earth traveling at the speed of light, aimed straight at that target. Will it ever arrive? Your first instinct is probably yes. After all, light travels at the fastest possible speed, and the galaxy is out there. Given enough patience, the photon should eventually reach it. If we simply wait long enough, surely it must. But this is where our intuition, calibrated on a static, unchanging world, fails us catastrophically. The space between your laser and the target galaxy is expanding. The photon does travel at the speed of light through the local space it happens to occupy, everywhere along its journey. That much is guaranteed by physics. But as the photon travels, the total distance to the target keeps growing. New space is constantly being created between the photon and the galaxy. In some cases, that new space is being created faster than the photon can close the remaining gap. When that happens, the photon is not gaining ground on its target. It is losing ground. It never arrives. Ever. No matter how long we wait, no matter what happens next, that photon will fall further and further behind the galaxy it was aimed at, until in the far cosmic future it fades into an infinite darkness, having never delivered its message. This is the shocking fact that separates the visible universe from the affectable universe. Under a cosmology dominated by dark energy, and under our current best understanding of how dark energy behaves, there is a boundary in space beyond which any signal launched today, at the speed of light itself, will never arrive. That boundary is called the cosmological event horizon, and its present-day proper distance sits at roughly 16 billion light-years, with a genuine uncertainty of several 100 million light-years depending on exactly which measurements of the expansion rate and dark energy you plug into the equations. Stop and let that number sit for a moment. 16 billion light-years. That is enormous by any human standard, but it is dramatically smaller than 46.5 billion light-years, which is the radius of everything you can currently see. The difference between what you can see and what you can ever influence is a factor of nearly 3 in radius, which becomes a factor of more than 20 in volume, because volume scales as the cube of the radius. Do the arithmetic honestly, and it turns out that under the standard cosmological model, only about 5% of the galaxies in the observable universe lie within humanity's causal reach. Only about 5% could ever, in principle, receive a message launched from Earth today. The remaining 95%, roughly 1.9 trillion galaxies, are visible to us in the sense that their ancient light is arriving now. But they are permanently beyond the reach of anything we could ever send. Their future is disconnected from ours. Their present, or what we would call their present, is not a place we can affect. It is a place we can only witness, and even those numbers, as we will see later in the journey, describe only the outermost limit, the case of a light-speed signal launched right now. Every step we take from a bare signal toward a physical probe, from a probe toward a crude spacecraft, from a spacecraft toward a lasting human settlement, will shrink that region further. Each step will shrink it dramatically. This is the shape of the story. Humanity's true frontier is nested inside layers, like a series of concentric shells, and each shell is much smaller than the one outside it. The outermost shell, the particle horizon, is what you can see. Inside it sits the event horizon, what you could ever affect. Inside that sits the region a real, physical craft could ever visit. Inside that sits the region living human beings could ever reach. And innermost of all sits the region where a recognizably human civilization, sustained across generations, could ever put down roots and stay. Before we go further, let us make sure we have named these categories with painful precision, because the entire rest of the story depends on keeping them distinct. The first level is receiving ancient light. This is the easiest form of contact, and the only kind we currently perform. We point a telescope, we collect photons, we learn about a place as it existed long ago. This tells us nothing about whether we can ever visit it. It only tells us the message got here. The second level is sending a signal that eventually arrives. This is not the same as level 1, and this is the source of endless confusion. Just because a place's light reached us does not mean our light can reach it. The arrival of ancient photons is a statement about the past. The delivery of a modern signal is a statement about the future. Under an expanding, accelerating cosmos, those are entirely different questions with entirely different answers. Many of the galaxies whose ancient light warms our detectors tonight are galaxies to which no signal we send today will ever arrive. The third level is delivering a robotic probe. Signals travel at the speed of light. Probes do not. Any physical object with mass must travel slower than light, and by how much slower depends on how much energy we can pour into accelerating it. Even a probe pushed to 99% of the speed of light travels appreciably slower than a raw photon, and over billions of years that difference becomes crushing. The region of the universe a probe launched today could ever reach is smaller than the region a light-speed signal could ever reach, sometimes dramatically so. The fourth level is delivering living humans, or beings recognizably descended from humans. Now we add biology. A crewed vessel must carry mass, life support, and the redundancy needed to keep fragile organic bodies alive across journeys that may last many human lifetimes. It must also decelerate at the far end if the goal is arrival rather than a flyby, and deceleration is nearly as costly as acceleration. The reachable region shrinks again. The fifth and final level is establishing a lasting settlement, a foothold that persists, that reproduces itself, that connects back through some fragile thread of civilization to the world it came from. This is the strictest test of all, and the region that satisfies it is the smallest of them. It is the region humanity could not merely visit, but truly inhabit, in a way that a future historian, looking back, would recognize as an outpost of our species. Every one of these 5 levels sits inside the one before it. Each is a smaller cosmic territory. Each answers a different question about what we can call ours, and every one of them is much, much smaller than what a telescope reveals to your patient eye. If you have not encountered this framing before, this is the moment where the sky changes shape. The night no longer feels like an open door. It feels like a window. You can see through it clearly. You can study what lies beyond it in exquisite detail. You can learn its chemistry, its evolution, its violent history and slow ballet. But most of what that window reveals is separated from you by more than distance. It is separated by geometry, by the very shape of space-time itself in a way that no engine can bridge. There is one more subtlety worth planting now, before we descend into the mechanics of expansion in the next part of our journey. It concerns the difference between speed through space and the expansion of space itself. This is the piece of physics that most often trips up newcomers, and it will matter enormously later. Einstein's relativity forbids anything from traveling through space faster than light, relative to a local observer. This is an ironclad rule, and it applies to spaceships, to signals, to information of any kind. But that rule says nothing about how fast space itself can stretch. Space is not a thing moving through anything else. It is the stage on which everything else moves. When 2 distant galaxies grow further apart because the space between them is expanding, neither galaxy is moving through space faster than light, at least not from its own local frame of reference. Yet the sheer amount of new space appearing between them can grow so large, so fast, that the distance between them opens up at a rate exceeding the speed of light. Not because anything is racing through the vacuum, because the vacuum itself is stretching. This is not a violation of relativity. It is a feature of general relativity, Einstein's theory of gravity, applied to a universe with a non-zero cosmological constant. And it is the reason the cosmological event horizon exists at all. If space were static, a light-speed signal would eventually reach any target, given enough time. In an expanding, accelerating universe, that is no longer true. New space keeps appearing between our signal and its target, and if the target is far enough away, that new space appears faster than the signal can traverse it. The signal falls behind. It stays behind. It stays behind forever. Which brings us to the last observation of this opening part of our journey. An observation that should quietly reshape how you feel about the night sky. Almost every galaxy you can see in a deep telescope image is receding from us. That much has been known since Edwin Hubble's work in the 1920s. But here is the subtler truth. Most of those galaxies are receding from us right now, in terms of proper distance, at speeds faster than light. That claim sounds impossible, and if it were about motion through space, it would be. But it is not. It is about how fast the total distance to those galaxies is currently increasing, because of expansion. The best current measurements suggest that any galaxy more than about 14.5 billion light-years away in present proper distance is receding superluminally in this sense. That radius, the boundary at which recession precisely matches the speed of light, is called the Hubble sphere, and its radius is about 14.5 billion light-years today. Notice something important. The Hubble sphere, at 14.5 billion light-years, is not the same as the cosmological event horizon at 16 billion light-years, and neither of them is the same as the particle horizon at 46.5 billion light-years. These three boundaries are often confused, even in serious writing, and untangling them is one of the essential tasks that lies just ahead in our journey. For now, plant this in your memory. There are galaxies currently receding faster than light that we can still reach with a signal. There are galaxies currently receding slower than light that we can never reach. The relationship between recession speed and reachability is not what your intuition expects, because the expansion rate itself changes over cosmic time. Once you understand why, you will understand almost everything about the shape of humanity's ultimate frontier. We began this part of the journey with a simple sky, a few thousand visible stars, a gentle promise that the universe stretches away in every direction, inviting exploration. We are ending it with something harder to accept. Only a small fraction of what shines above us is territory we could ever reach, in any sense, at any speed, using any technology, across any span of time. The rest is scenery. Beautiful scenery, ancient scenery, scientifically invaluable scenery, but scenery all the same, places we can study but never touch, places whose future is separated from ours by the very geometry of the cosmos we share. To understand why that geometry works this way, and to nail down exactly where the boundaries fall, we need to look closely at expansion itself. We need to see how a beam of light behaves in a universe that is stretching underneath it. We need to distinguish the three horizons that shape our cosmic reach and understand why dark energy, more than any engine, sets the true limit on humanity's future. That is where the next stage of our journey takes us, into the strange, counterintuitive machinery of an expanding, accelerating cosmos, and into the geometry of the cage we do not usually realize we are inside. To understand why humanity's frontier is so much smaller than the visible sky, we have to understand what the universe is actually doing when we say it is expanding. That word, expansion, is one of the most misused terms in all of popular science. People imagine galaxies flying outward through some pre-existing void, like debris from an explosion, hurled through empty space by the primordial detonation of the Big Bang. That picture is wrong in a way that changes everything that follows. If galaxies were simply flying through a static space, the entire question of what humanity could reach would collapse into simple arithmetic. Distance divided by speed. Given enough time, everything would eventually be accessible to a sufficiently patient traveler. There would be no permanent horizon, there would be no cage. But the universe is not doing that. It is doing something stranger, and to see why, we have to understand a single elegant idea. Space itself has a size, and that size is changing. Picture the surface of a balloon with dots drawn on it in permanent ink. Each dot represents a galaxy. The dots do not move across the surface of the balloon. They are stuck to the rubber. Now inflate the balloon. Every dot stays exactly where it was drawn. In terms of the local rubber it is glued to, yet the distance between any two dots grows. From the perspective of any single dot, every other dot appears to be receding, and the more distant dots recede faster than the nearer ones, because there is more stretching rubber between them. No dot is at the center. No dot is moving through anything, and yet the distances between them all increase, because the surface beneath them is expanding. This is roughly what our three-dimensional universe is doing. Galaxies are not, for the most part, moving through space at high speeds. They sit relatively still in their local patch of the cosmos, held in place by the gravity of their own neighborhoods. What is happening is that the space between distant galaxies is stretching. New space appears between them, everywhere, all the time, and the further apart two galaxies are, the more stretching rubber sits between them, and therefore the faster they appear to recede from one another. This gives us a simple, powerful rule discovered by Edwin Hubble in the 1920s. The recession speed of a galaxy is proportional to its distance. Twice as far away means twice as fast. 10 times as far away means 10 times as fast. Push this relationship far enough, and you arrive at a distance where the implied recession speed equals the speed of light itself. That distance is called the Hubble radius, and today it sits at roughly 14.5 billion light-years. Galaxies at that distance are receding from us at exactly the speed of light, right now. Galaxies further away are receding faster than light. Galaxies closer are receding slower. If your instincts are screaming that this violates Einstein's rule about nothing traveling faster than light, take a breath. It does not. Einstein's rule forbids anything from moving through space, past a local observer, faster than light. But the recession of distant galaxies is not motion through space. It is the expansion of space itself. Nobody is racing past anyone. The rubber between the dots is stretching. That is a very different thing, and it obeys entirely different rules. This distinction is not a technicality. It is the reason the entire story of humanity's reach is stranger than most people realize. A galaxy receding from us faster than light is not automatically unreachable, and a galaxy receding slower than light is not automatically reachable. Under an accelerating expansion, both statements can be true, and both are wildly counterintuitive. To see why, we now have to introduce the three horizons that shape our cosmic reality. Three distinct boundaries, each answering a different question, and each sitting at a different radius in the sky. The first horizon is the particle horizon, and we met it briefly a little earlier in our journey. It is the boundary between sources whose light has already reached us, and sources whose light has not yet arrived. Its present proper distance is about 46.5 billion light-years. Everything inside that boundary is what we call the observable universe. It is the region from which any information at all has arrived at Earth since the beginning of cosmic time. When you look at the Hubble Ultra Deep Field or a Webb Deep Field image and count galaxies, you are counting objects inside the particle horizon. The second horizon is the Hubble sphere. Its radius, today, is about 14.5 billion light-years in proper distance. Every galaxy currently more distant than the Hubble radius has, at this very moment, a recession speed that exceeds the speed of light due to the stretching of space between us and it. Every galaxy closer than the Hubble radius has, at this moment, a recession speed less than the speed of light. The Hubble sphere is often confused with the boundary of reachability, but it is not that boundary at all. It is simply a snapshot of where the recession equals light speed line falls today. The third horizon is the one that matters most for humanity's frontier, and it is the one most people have never heard of. It is called the cosmological event horizon. Its present proper distance is roughly 16 billion light-years. This horizon is not about where light has come from, and not about where recession matches light speed today. It is about where, if we send a signal right now, that signal can ever eventually arrive. Any target inside the event horizon can, in principle, be reached by a light speed signal launched today if we wait long enough. Any target outside the event horizon cannot ever be reached by a signal launched today, no matter how long we wait, no matter what technology we invent, no matter what future we build. These three horizons are all different, And understanding why is the key to understanding what humanity can and cannot ever affect. Notice something strange right away. The Hubble sphere sits at 14.5 billion light-years. The event horizon sits at 16 billion light-years. The event horizon is further away than the Hubble sphere. That means there are galaxies currently receding from us faster than light, sitting between 14.5 and 16 billion light-years away, whose future we can still touch. A signal we send today can still reach them, even though the distance to them is increasing faster than the signal itself can travel. Right now. How is that possible? The answer is beautifully subtle. The photon we send today is currently losing ground, yes. New space is opening up between it and its target faster than the photon can traverse the intervening distance in the current moment. But the expansion rate is not the same at all points along the photon's future journey. As the photon travels outward, it enters regions where the local Hubble expansion, once you correct for the target's motion, allows it to gain ground. Over cosmic time, the balance shifts. The photon eventually catches up. The signal arrives. It just takes a mind-numbing amount of time to get there, sometimes tens or even hundreds of billions of years, and it arrives at a galaxy that has by then receded to a proper distance vastly greater than 16 billion light-years. But it arrives. To make this concrete, imagine a photon launched today toward a galaxy sitting at 15 billion light-years of present proper distance. This galaxy is inside the event horizon, but just barely, and it is currently receding from us at slightly faster than the speed of light. For the first billion years of its journey, the photon is genuinely falling behind. The gap between it and its target actually widens, even though the photon is traveling at the speed of light in the local space it occupies. From an outside perspective, this looks like a hopeless chase. The runner is slower than the runaway target, and the distance between them keeps opening up. But something quietly changes as billions of years pass. The photon is moving into regions of space where, relative to those local regions, the target galaxy is receding at a lower speed. This is because in the cosmological description used by physicists, the relevant recession speed is not measured relative to Earth. It is measured relative to the local patch of space the photon is currently traversing, and as the photon advances outward, the local frame it occupies begins to catch up with the frame the target galaxy occupies. The gap starts to close, slowly at first, then more decisively. Eventually, after perhaps 50 or 70 or 100 billion years, depending on precise conditions, the photon crosses the last remaining distance and arrives. By the time it arrives, the target galaxy has receded, in proper distance from Earth, to something far greater than 15 billion light-years, perhaps hundreds of billions of light-years, perhaps trillions. The photon is delivered to a galaxy that is no longer where it appeared to be when the message was sent, but it is delivered nonetheless. This is the counterintuitive triumph of a photon inside the event horizon, and it is the reason the boundary of reachability sits further out than the boundary where recession equals the speed of light today. Now consider a galaxy sitting just outside the event horizon, at, say, 17 billion light-years of present proper distance. This galaxy is receding faster than light today, exactly like the 15 billion light-year target. But this time, the expansion of space between us and it grows too quickly forever. Every year, more new space appears between the photon and the target than the photon can bridge. The photon's shortfall grows and grows. It never closes the gap. It never arrives. Ever. And no future engineering, no future technology, no future civilization can rescue it, because the shortfall is baked into the geometry of space-time itself. This is the cage. This is the boundary that defines humanity's ultimate frontier. Not the particle horizon at 46.5 billion light-years, not the Hubble sphere at 14.5 billion light-years, the cosmological event horizon at roughly 16 billion light-years of proper distance today. Take a moment to feel the weight of this. Of the 2 trillion galaxies inside the observable universe, only a small fraction sit inside the 16 billion light-year event horizon. When you do the calculation honestly, using the volumes of the 2 spheres and the average distribution of galaxies inside them, you find that only about 5% of visible galaxies fall inside the region we could ever affect, even with a signal moving at the ultimate speed of the cosmos. 95% of what you can see, roughly 1.9 trillion galaxies, are already beyond us. Their futures are severed from ours by the very geometry of the universe we share. But before we move on, we have to answer a critical question. What creates the event horizon in the first place? Why does one exist at all? In a universe with no dark energy, where cosmic expansion was slowing down because of the gravitational pull of matter, the answer would be different. In that universe, a light-speed signal launched today could eventually reach essentially any target, given enough patience. There would be no permanent line. The particle horizon would grow forever, revealing more and more of the cosmos, and humanity's ultimate reach would be limited only by biology, engineering, and time. It would not be limited by geometry. The event horizon exists because our universe is not just expanding, it is accelerating. And it is accelerating because of dark energy. Dark energy is the placeholder name we use for whatever is causing the expansion of the universe to speed up over cosmic time. It was discovered in the late 1990s when two independent teams of astronomers, studying distant supernova explosions as standard cosmic markers, realized that the light from those explosions was fainter than it should be if the universe were expanding at a constant rate or slowing down. The only reasonable interpretation was that the universe's expansion had been accelerating for the past several billion years, driven by some unknown component that behaves like a form of energy woven into the fabric of empty space itself. The discovery earned the Nobel Prize in Physics in 2011 and rewrote our understanding of the cosmos. Under the current best-fit model, called lambda cold dark matter, dark energy makes up about 69% of the total energy content of the universe. Matter, both ordinary and dark, makes up the rest. If dark energy is truly a cosmological constant, meaning it has the same value everywhere and at all times, then the fate of the universe is essentially locked in. Expansion will continue accelerating forever. The event horizon will remain roughly where it is now, 16 billion light-years away in proper distance, defining a permanent frontier around what humanity could ever influence. Everything currently outside that frontier is lost to us forever. Everything currently inside remains, in principle, reachable by a light-speed signal, if we act on that possibility soon enough. But here is where the story acquires a genuine, honest uncertainty, and honesty demands we name it clearly. In the last several years, new observations from the Dark Energy Spectroscopic Instrument, known as DESI, have hinted that dark energy might not be exactly constant after all. The DESI collaboration has released results, most recently in 2024 and 2025, suggesting that when its data is combined with other cosmological measurements such as the cosmic microwave background and Type 1a supernovae, there is a preference, at statistical significance in the range of 2 to nearly 4 standard deviations depending on the analysis, for a dark energy that evolves over cosmic time. Specifically, the results hint at a dark energy that was somewhat stronger in the past and may be weakening today. That is not a confirmed discovery. It is a candidate result, and the community remains cautious. 2 to 4 standard deviations is intriguing but not conclusive. Systematic effects, calibration questions, and statistical interpretation issues could shift the picture as more data arrives from DESI itself, from the Euclid Space Telescope, and from other upcoming surveys. If the effect turns out to be real, it would change our answer about humanity's frontier in ways we will explore carefully later on. If it turns out to be a statistical fluctuation or a systematic artifact, the standard cosmological model, with its constant dark energy, remains the best description we have. For the remainder of our journey through the physics, and for most of what follows, we will treat the standard model as our reference case. It is the most conservative choice. It is consistent with essentially all major observations, and it gives us a concrete framework inside which we can calculate everything else. We will return to alternative dark energy scenarios later. Under the standard model then, here is the picture. The event horizon at 16 billion light-years defines the absolute causal limit for anything launched from Earth today. Beyond that boundary, no signal, no probe, no message, and no traveller could ever arrive. Inside that boundary lies the region humanity could, in principle, affect. And within that region, we now need to ask a much sharper question. Not how far a light-speed signal could go, but how far a physical craft, a probe or a settlement, could actually reach. This is where we begin to see why the frontier of what we could ever influence, the region a signal could cross, is very different from the region a physical spacecraft could cross. And to see the difference, we need to think carefully about what a spacecraft actually has to do. A light-speed signal is a photon. It has no mass, no fuel requirements, no life support, and no need to slow down at the end of its journey. It leaves Earth and travels at the speed of light through the local space it happens to occupy at every point along its path. Nothing needs to be accelerated. Nothing needs to be decelerated. The photon's journey is the simplest possible cosmic voyage. A spacecraft is nothing like a photon. It has mass. Every gram of that mass has to be accelerated up to whatever fraction of light speed the mission requires, and doing so costs energy. If the mission is to arrive rather than to fly by, the spacecraft has to be decelerated at the destination, which costs another comparable amount of energy. The faster the spacecraft has to go, the more brutal the energy cost becomes, and the cost is not linear. It rises steeply and then hyperbolically as the craft's speed approaches the speed of light, because relativistic effects mean that pushing an object closer to light speed requires ever-increasing amounts of energy per additional increment of velocity. Reaching 90% of light speed is difficult. Reaching 99% is much harder. Reaching 99.9% is harder still. And the light speed limit itself is unreachable in principle for any object with mass. Suppose, for the sake of argument, that humanity develops a technology that can push a probe to some large fraction of the speed of light, perhaps 80%, perhaps 90%, perhaps even, in an extraordinary future, 99% using something like a beamed laser sail, an antimatter engine, or a fusion-driven ramjet. What does this actually get us in terms of reach? The answer is that even a 99% light-speed probe launched today falls behind a photon launched today, and the shortfall grows over cosmic time. A photon reaches, in principle, everything inside the event horizon at 16 billion light-years. A 99% light-speed probe reaches a smaller region, because at every point along its journey, it is losing ground to the photon by 1% of the traversal speed. Over billions of years, that gap becomes enormous. The probe arrives at fewer galaxies than the photon does. Many galaxies that a light-speed signal launched today could reach are galaxies that the probe cannot reach. The reachable region shrinks. If the probe travels at 90% of light speed, the reachable region shrinks further. At 50% of light speed, it shrinks dramatically. At the speeds of realistic future propulsion technologies we can imagine today, using known physics, the reachable region collapses towards something much smaller than 16 billion light-years. We will explore just how much smaller in the pages ahead, and there is one more penalty that most people never consider. It is called the delay penalty, and it is one of the most sobering ideas in the entire discussion of humanity's future reach. Every year humanity waits before launching, the reachable region shrinks. Every year, expansion continues. Every year, the universe becomes a little larger, and a little more of what we could have reached slides beyond the event horizon and becomes forever lost. The rate of loss is not enormous on human timescales, but it is not zero either. Over thousands of years of delay, over millions of years of delay, the loss compounds. A probe launched today can reach some galaxy at the very edge of the affectable region. A probe launched 1 million years from now, aimed at the same galaxy, cannot reach it. In the intervening million years, that galaxy has receded past the event horizon relative to a launch performed at the later time, because the event horizon effectively shrinks in the co-moving frame as time passes and expansion continues. This is one of the most philosophically strange facts about our cosmological situation. Every generation of humanity, or any successor civilization, that delays departure loses potential territory. The universe does not wait, it expands regardless of what we do. And the horizon of what we could ever touch, if we ever chose to try, is receding slowly but relentlessly every year we remain on Earth. Notice what this implies. The question of humanity's reach is not just a question of physics and engineering, it is also a question of timing. A civilization that expands early can reach places a civilization that expands late cannot. A civilization that never expands at all can, in principle, still affect the region inside the current event horizon, but only by launching signals or automated probes on some cosmic timescale. There is a window. It is enormous by human standards, tens or hundreds of billions of years wide, but it is not infinite. And the sooner within that window we choose to move, the larger the territory that remains available to us. Before we close this stage of our journey, we should notice one more thing. Everything we have said so far is about the absolute causal frontier, the outer limit set by the speed of light and the geometry of expanding space-time. This is the largest possible cosmic domain humanity could ever affect. It is the outermost shell of the nested picture we sketched earlier, and even this outermost shell, the region a photon launched today could ever reach, contains only about 5% of the galaxies we can see, roughly 100 billion galaxies. A vast number, larger than any mind can properly hold, and yet dwarfed 20 times over by what we can observe but cannot touch. Everything from here onward will be about moving inward, through the nested shells. From the causal frontier of a signal to the reach of a probe, from the reach of a probe to the reach of a crewed ship, from the reach of a crewed ship to the reach of a lasting settlement. Each step will shrink the territory. Each step will make the answer smaller. And each step will bring us closer to the true answer to our question, which is not what humanity could see or send a message to, but what humanity, as a living, self-sustaining, recognizably human civilization, could ever really call home. That is where our journey turns next, into the difficult, humbling territory of what happens when you replace a beam of light with a physical ship carrying beings who must survive the crossing. We now stand at the outer boundary of humanity's causal reach. The cosmological event horizon, sitting at roughly 16 billion light-years of present proper distance, defines the absolute frontier of anything we could ever influence, using any technology whatsoever, up to and including a signal traveling at the exact speed of light. Inside that boundary sits a region containing about 100 billion galaxies. Outside it lies more than 1.5 trillion galaxies whose futures are permanently severed from ours. No matter what we ever build, no matter what we ever launch, no matter what we ever attempt. That number, 100 billion galaxies, is astonishing by any human standard, and yet it is only the outermost shell of our nested picture. Everything we have described so far assumes a signal moving at the speed of light itself, and that assumption is generous in the extreme. It ignores the physical realities of building a spacecraft. It ignores the biology of the beings who might ride inside such a spacecraft. It ignores the fragile institutional continuity required to sustain a civilization across cosmic time. We now begin the long, humbling process of moving inward through the shells, from the causal frontier down through the practical frontier, and eventually to the region humanity could truly inhabit. Start with the simplest possible upgrade beyond a bare signal, which is an automated probe. A signal carries information but nothing else. A probe carries information, mass, instruments, and the ability to act at its destination. Even the simplest probe, a robotic explorer with no crew, must overcome an obstacle that a photon never encounters. It must be accelerated up to whatever fraction of the speed of light it will travel at, using energy carried aboard or delivered from outside, and every ounce of mass it carries multiplies that energy cost. Let us start optimistically. Imagine that some future civilization has developed a propulsion system capable of accelerating a probe to 99% of the speed of light. This is far beyond anything humanity can currently achieve, but let us grant it for the sake of argument. How much of the causally accessible region can such a probe reach? The answer is smaller than most people expect. Under the standard cosmological model, a probe launched today at 99% of light speed can reach essentially every galaxy that lies well inside the event horizon, but it falls short at the edge. Any galaxy sitting near the causal boundary, where a photon would just barely arrive after tens or hundreds of billions of years of travel, is a galaxy the 99% probe cannot reach at all. The photon is faster. That 1% shortfall, compounded across cosmic time, is enough to lose the outermost shell of the affectable region entirely. The probe's reachable universe is smaller than the photons by a noticeable margin, but not catastrophically so. Perhaps 95% of the galaxies a light-speed signal could reach are also reachable by the 99% probe if we are willing to wait long enough for arrival. That still leaves us with roughly 95 billion galaxies inside the practical frontier of a near-light-speed automated probe. Now, drop the speed. Suppose our probe travels at 90% of light speed. The reachable region shrinks noticeably. Perhaps 80 billion galaxies remain accessible, again allowing for arrival times measured in tens of billions of years. Drop the speed to 50% of light speed. The reachable region collapses further, down to perhaps 40 or 50 billion galaxies. Drop it to 10% of light speed, which is closer to what near-term physics might realistically permit using something like a beamed laser sail, and the number falls further still. The frontier for a slow probe is only a fraction of what a photon could achieve, because every year of slower travel is a year during which the target galaxy has receded further, sometimes enough to slide past the effective boundary entirely. To make this concrete, consider a specific example. Suppose we aim a probe at a galaxy currently sitting 8 billion light-years away in proper distance, well inside the event horizon. A photon launched today would reach that galaxy after tens of billions of years, arriving at a galaxy that has by then receded to a proper distance far greater than 16 billion light-years. A 99% light-speed probe launched today reaches the same galaxy roughly 1% later, which sounds trivial until you realize that 1% of a 100 billion-year journey is an entire billion years of extra travel time, during which the target has receded further and the trajectory has to be recomputed. A 50% light-speed probe takes double the light travel time, and by the time it arrives, the target galaxy is far more distant than it would have been for the photon. A 1% light-speed probe cannot arrive at all in most cases, because the target galaxy recedes faster than the probe can advance for most of the journey. There is a general lesson here. Physical travel through the cosmos is dominated not by ordinary intuition about speed and distance, but by the interplay between how fast you can move and how fast the space between you and your target is stretching. Below a certain threshold speed, most galaxies become unreachable in principle, even those well inside the event horizon. Above that threshold, you can reach a large fraction of the causal region, but you never reach quite as far as light itself does. There is a second obstacle facing any physical probe that most casual discussions of interstellar travel simply skip over, and it deserves to be named clearly. It is the problem of deceleration. Reaching a distant target is not the same as arriving there. A probe that streaks past its target galaxy at 50% of the speed of light has not, in any meaningful sense, arrived. It has, at best, taken a fleeting glimpse of the destination on its way to somewhere else. If the purpose of the mission is to explore, to build, to settle, or to establish any lasting presence, the probe must slow down. It must dump the enormous kinetic energy it acquired during acceleration, and it must dump it in a way that leaves the probe intact and functional at the far end. This problem is not a minor detail. It roughly doubles the energy budget of any interstellar mission, because slowing down from a given fraction of light speed requires essentially the same magnitude of energy as speeding up to that fraction in the first place. And unlike acceleration, deceleration cannot always be accomplished by carrying fuel. If a probe is boosted to relativistic speed by an external system, such as a giant laser array anchored in our solar system, that external system cannot help at the far end. The probe is alone. It must carry its own deceleration mechanism or find one at the destination, or accept that it will never truly arrive. There are proposals for how to solve this problem. Magnetic sails could, in principle, use interstellar or intergalactic plasma as a braking medium, converting kinetic energy into gentle deceleration over long distances. Reverse thrust rockets could carry their own fuel for the slowdown, though this multiplies the initial mass problem enormously. Beamed laser deceleration from a station previously established at the destination would work, but requires that we have already sent something ahead. Every one of these proposals introduces complications that shrink the practical reach of interstellar missions further, and none of them are on the near horizon of engineering feasibility. When we say that a probe could reach a galaxy at 50% of light speed, we are quietly assuming a solution to the deceleration problem that we do not currently possess. Now let us return to the delay penalty, because when we begin to attach concrete numbers to it, the picture sharpens in a way that changes how the whole story feels. Imagine humanity, or its descendants, wait 1,000 years before launching a serious interstellar expansion effort. On cosmological timescales, 1,000 years is essentially nothing. The event horizon does not visibly move. The number of galaxies inside the causal region shifts by an amount too small to matter. From the practical standpoint of what we could reach, a 1,000-year delay costs us essentially nothing. Extend the delay to 1 million years. Now, the picture starts to change. In 1 million years, the universe continues expanding at its current rate, and galaxies at the edge of the affectable region drift outward by roughly 1 million light-years in proper distance. This is a small fraction of the 16 billion light-year event horizon, but it is enough to push some marginal targets across the effective boundary relative to a launch performed at that later time. The number of galaxies that fall outside the delayed launch's effective reach is not huge, perhaps a few tens or hundreds of thousands, still small in relative terms, but no longer zero. Extend the delay to 100 million years. Now we are losing perhaps a percent or two of the previously accessible galaxies. On the outer edges of the affectable region, entire shells of targets slide away, and probes launched at that later date can no longer make up the additional distance the universe has opened up in the meantime. The loss compounds because the shells being lost are shells at the edge of reachability, where the physics of the chase is already marginal, and even a small increase in the starting distance can be enough to tip a target from barely reachable to permanently unreachable. Extend the delay to 1 billion years, and the losses become severe. Under the standard cosmological model, roughly 10% of the currently reachable galaxies would no longer be reachable by probes launched at that time, because the accelerating expansion has continued for a full billion years, and the effective horizon has meaningfully contracted. Extend the delay to 10 billion years, and the affectable region shrinks by a factor of several. Extend it to 50 or 100 billion years, and the losses become catastrophic. Far into the cosmological future, the effective horizon relative to a delayed launch shrinks towards something close to the local group of galaxies, and essentially everything else becomes permanently beyond reach. The point of walking through these numbers is not to sound an alarm. On human timescales, and even on timescales relevant to any conceivable version of the near future of our civilization, the delay penalty is not a pressing concern. 1 million years of delay is nothing in the life of a species that has been technologically capable for only a few thousand years. The universe is not tapping its watch. But the principle is real, and it becomes real in a way that matters if we ever imagine a civilization capable of persisting across geologic or cosmic time. A civilization that endures for 100 million years, or 1 billion, and chooses only in its final chapters to begin expanding outward, will find that vast territory that once was available has quietly slipped beyond every possible journey. Now let us add the next layer of difficulty. Replace the probe with a crewed vessel carrying living beings. A crewed spacecraft is a different animal from a probe, and not in any trivial way. It must carry life support, shielding against radiation, food, water, waste recycling, redundant systems, medical facilities, and the physical infrastructure to sustain conscious biological beings across a journey that may last many human lifetimes. All of this mass has to be accelerated, decelerated, and sustained. The energy cost of pushing a crewed vessel to relativistic speeds is enormously greater than the cost of pushing a bare probe to the same speed, because the crewed vessel is enormously more massive. Every ton of shielding, every ton of consumables, every ton of habitat structure must be pushed to that same fraction of light speed and then slowed to rest at the destination. But the mass and energy problems are not the only difficulties. There is also the problem of survival. A vessel travelling at 99% of the speed of light through the interstellar and intergalactic medium encounters ordinary hydrogen atoms, dust grains, and cosmic ray particles at an apparent energy equivalent to gamma radiation. Every atom in its path becomes a projectile. Shielding against this bombardment across a journey of tens of billions of years is not a solved problem. or even a well-posed one. It is not obvious that a crewed vessel could survive relativistic travel at such speeds across such durations, even if we could accelerate it in the first place. Then there is the problem of biological continuity. Human beings live, at best, about a century. A journey across cosmic distances, even at relativistic speeds, will span many generations from the perspective of the crew. Time dilation helps here. A crew travelling at 99% of light speed experiences roughly 1/7 of the elapsed time on the ship, compared to an outside observer. At 99.9%, the ratio is about 1/22nd. At 99.99%, roughly 1/70th. Push these numbers and you can, in principle, cross vast cosmic distances within a single crew lifetime, from the perspective of the travellers. But the outside universe, and everything they left behind, ages tens or hundreds of billions of years. Whatever civilization launched them will have been transformed beyond recognition, or ended entirely, long before they arrive. For crews travelling at speeds too low for meaningful time dilation, the picture becomes worse in a different way. Generation ships, vessels carrying a self-sustaining human community across journeys lasting thousands or millions of years, must maintain a functioning society, a functioning ecosystem, and a functioning technology base across timescales that no human civilization has ever come close to matching. The oldest continuous human institutions on Earth measure their durations in mere millennia, and every one of them has undergone repeated crises, reinventions, and near collapses. A generation ship must succeed at cultural, biological, and mechanical continuity across timescales dwarfing all recorded history. Whether this is achievable is not a question physics can answer. It is a question of biology, sociology, and long-term engineering resilience. There is a further complication that shapes what any crewed mission could ever accomplish, and it concerns communication rather than travel. When a probe or a crewed vessel departs Earth for a target billions of light-years away, the very act of departure severs any meaningful conversation with the mission's origin. A message sent from Earth to a probe already several billion light-years out, at the moment of transmission, would need billions of years to arrive, if it could arrive at all. A reply would need billions more. There is no back and forth. There are no course corrections. There is no rescue mission. Whatever the probe or the crew takes with them at launch is essentially everything they will ever have from home. For a settlement, this problem becomes even stranger. A colony founded on a planet 10 billion light-years from Earth is, from Earth's perspective, receiving instructions and news that are 10 billion years out of date, if any signals arrive at all. And Earth, from the colony's perspective, is a place whose current condition is unknowable in principle, because no information from Earth's current moment can travel faster than light. The colony and its parent world are, in every meaningful sense, separate civilizations from the instant of arrival. They cannot cooperate, they cannot coordinate, they cannot trade in real time. They can, at most, exchange packets of ancient information that arrive across geological or cosmological timescales, and each side must interpret the other's messages as historical documents rather than as ongoing conversation. This is why the fifth level of our nested hierarchy, the level of lasting settlement, is such a strict test. A settlement is not merely a crew that arrived, it is a civilization capable of surviving without contact, without rescue, without the parent world's resources, and without any prospect of meaningful reunion. Every settlement founded across cosmic distances would be its own island, and the island metaphor is almost too generous, because islands on Earth at least share weather patterns and ocean currents with the mainland. A settlement in another galaxy shares nothing with Earth except a common ancestry that stretches back across a gulf of time and space, too large for any communication to bridge. There is one further dimension of this problem worth naming, and it concerns the shrinking local group, our own gravitational neighbourhood, the local group of galaxies containing the Milky Way, Andromeda, Triangulum, and dozens of smaller companions, is the one region of space where cosmic expansion has effectively already lost. Gravity binds the local group together tightly enough that expansion cannot pull it apart, and the whole system behaves as a single gravitational island floating in an ocean of accelerating expansion. Far into the future, when everything outside the local group has receded beyond the observable horizon, the local group will remain a single, connected, gravitationally bound structure. This makes it the one region where a civilization could establish settlements that remain in causal contact with each other essentially forever, without expansion tearing the connections apart. Everything outside the local group is a one-way journey into permanent separation. Everything inside remains, in some meaningful sense, a shared cosmic neighborhood. The distinction matters because it defines the innermost, most robust core of any possible human future, and it may well be that the true settled domain of humanity ends up being not the whole affectable region, but this one gravitationally bound cluster of galaxies that expansion cannot ever take away from us. All of these constraints combine to shrink the region humanity could actually reach with crewed vessels well below the region reachable by an automated probe. Even under optimistic assumptions, the crewed frontier is probably at least an order of magnitude smaller than the probe frontier in volume, and possibly much more. But we are not yet at the innermost shell. Beyond even the crewed frontier lies the region of actual settlement, which is smaller still. To settle a galaxy is not merely to visit it. It is to establish a lasting presence there. It is to place human beings, or beings descended from humans, in a functioning outpost that can sustain itself across generations, that can produce a next generation of settlers, and that can, ideally, contribute to the further expansion of the settled region. Settlement is not a single event. It is the beginning of a self-sustaining process. And a self-sustaining process requires a functioning ecosystem, a functioning economy, and a functioning technological base, all of which must be assembled from local resources at the destination. This is a difficulty most casual discussions gloss over entirely. When people talk about interstellar colonization, they often imagine that arriving at a habitable world, or a suitable barren world, is the hard part. Once you are there, the rest is a matter of local engineering. But the actual challenge is much greater. A settlement must be self-sufficient because it is disconnected from Earth by communication delays of billions of years. There will be no resupply. There will be no technical support. If a critical component fails, the settlement must be able to manufacture a replacement from local materials, using local energy with local expertise. If the ecosystem collapses, the settlement dies. If the human population falls below viability, the settlement dies. If the technology base slips even one significant step, the settlement dies. The reach of a self-sustaining settlement front, then, is even smaller than the reach of a crewed vessel, because the payload requirements are enormous. A settlement mission must carry not just a crew, but the raw materials, the manufacturing capacity, and the biological diversity needed to establish a viable outpost from scratch. All of this must be accelerated, decelerated, and delivered intact. There is, however, a clever strategy that partially escapes some of these constraints. It is the idea of self-replicating probes, sometimes called von Neumann probes after the mathematician John von Neumann, who first analysed the general concept. The idea is straightforward, at least in outline. Instead of sending a single large mission to a distant target, we send a small automated probe capable of reaching a nearby star system, harvesting local resources, and building copies of itself. Each copy then departs for its own set of targets. The number of probes grows exponentially, and the expansion front of the probe network can, in principle, sweep across an enormous region of the cosmos, far faster than any single vessel could reach even one target. Self-replicating probes have a critical advantage. They do not need to carry the mass of a full civilization across cosmic distances. They only need to carry the mass of a single self-replicating unit, along with the design specifications for whatever it is intended to build at each destination. The rest is manufactured locally. This slashes the energy cost of each individual mission enormously, and it means that the expansion front can advance at a speed limited primarily by the speed of the individual probes rather than by the cost of each stage. If a civilization can build self-replicating probes and launch them at, say, 10% of the speed of light, the expansion front spreads across the affectable region at 10% of the speed of light. Over a few tens of billions of years, such a front could sweep across a substantial fraction of the causally accessible universe. If the probes are capable of establishing habitats and eventually delivering human genetic material or embryos for reconstitution at destinations, the settlement front could, in principle, follow behind. This is speculative, and it depends on technologies we cannot presently build, but it is not obviously impossible under known physics, and it represents the most optimistic, realistic strategy for maximizing humanity's cosmic footprint. There is a strange implication buried in this idea, and it is worth pausing to name it clearly, because it touches on one of the deepest puzzles in modern astronomy. If self-replicating probes are physically possible, then any technological civilization that arose significantly earlier than us, anywhere within our causal region, should have already launched such a front. The expansion at 10% of the speed of light is fast on cosmic timescales. A civilization that began its expansion just a few 100 million years before us would, by now, have swept its probes across enormous volumes of nearby space. Their outposts, their machines, their engineering signatures should already be visible in our sky, and yet, when we look, we see none of this. We see galaxies that behave as raw physics predicts, undisturbed by any obvious sign of large-scale engineering. We see no swarms of infrared waste heat from Dyson-style megastructures. We see no unnatural patterns in the distribution of light across nearby superclusters. We see, as far as our best instruments can tell, an untouched cosmos. This absence is one form of what physicists call the Fermi paradox, and our reachability calculations sharpen it into something uncomfortable. If the affectable region contains 100 billion galaxies, and even a tiny fraction of them ever produce civilizations capable of self-replicating probe technology, we should see evidence of expansion fronts already in motion. We do not. There are several possible explanations. Perhaps intelligent life is far rarer than we assume, and we are among the first in our causal region. Perhaps civilizations reliably destroy themselves before they can launch such fronts. Perhaps the technology is far harder than it looks on paper, and no civilization ever builds it. Perhaps expansion is possible, but almost no civilization chooses to attempt it, either because it becomes philosophically uninteresting to advanced minds, or because there is some reason to prefer confinement. None of these possibilities are comforting, and none of them are decisive. But the calculation we have just walked through means that our own possible expansion is not just a story about the future, it is also a piece of data about the past. Whatever we eventually choose to do or fail to do about crossing into the wider, affectable region, our decision will echo through the same physics that has, so far, remained silent everywhere we look. Even so, even under the most optimistic assumptions about self-replicating probes and downstream settlement, the reachable settlement region falls well short of the causal region. A probe expanding at 10% of the speed of light, starting today, could over the next 100 billion years reach perhaps a few billion galaxies, in a rough order of magnitude estimate. That is a magnificent number, larger than any individual mind can properly hold, but it is only a few percent of the galaxies inside the event horizon, and it is a small fraction of 1% of the galaxies inside the observable universe. Now let us return to the delay penalty, the sobering fact we introduced a little earlier, because it has serious teeth once we start talking about physical spacecraft. Every year humanity waits before launching interstellar probes, the reachable region shrinks. For a light-speed signal, the shrinkage is small in the near term. For a physical probe traveling at a fraction of the speed of light, the shrinkage is more severe, because the probe has to make up the additional distance that the target has receded during the delay. A galaxy that a 10% light-speed probe could reach if launched today may be unreachable if launched a million years from now, because in the intervening million years, the target has receded by an additional million light-years or so of proper distance, and the probe now has to make up that additional gap on top of everything else. Compound this across long delays, and the settlement frontier shrinks measurably, even on timescales that seem generous by human standards. A civilization that begins its expansion 100 million years from today has access to substantially less territory than a civilization that begins today. A civilization that waits a billion years finds its accessible settlement region dramatically reduced, and a civilization that waits several billion years discovers that vast portions of what it might once have reached have slipped away entirely, carried off by the accelerating expansion of the universe. There is a deeper point buried in this arithmetic. The The universe is not waiting for us to make up our minds. The frontier of what humanity could ever affect is not a fixed target. It is a receding one, shrinking every year, every century, every millennium. The longer any civilization remains confined to its home system, the smaller its ultimate cosmic footprint becomes, even if that civilization eventually acquires godlike engineering capabilities. Speed matters, but so does timing, and nothing in the physics of expansion allows us to recover territory once it has passed beyond the effective horizon relative to a later launch time. Let us now step back and put numbers on the nested shells we introduced earlier, at least in rough order of magnitude, so we can see the whole shape of humanity's frontier clearly. The outermost shell is the observable universe. Its radius is roughly 46.5 billion light-years in proper distance. It contains about 2 trillion galaxies. This is what we can see. It is not what we can reach. The next shell inward is the causal region defined by the cosmological event horizon, at roughly 16 billion light-years of proper distance under the standard model. It contains about 100 billion galaxies, about 5% of the visible universe. This is the region a light speed signal launched today could ever affect. It represents the absolute upper bound of humanity's cosmic reach, and no technology of any kind can extend it, because it is set by the geometry of space-time itself. Inside that shell sits the region reachable by automated probes at some realistic fraction of the speed of light. If we assume a highly optimistic 99% light speed probe, this shell captures perhaps 95% of the causal region, on the order of 95 billion galaxies. If we assume more modest speeds, say 10% of light speed, the shell shrinks to perhaps a few billion galaxies. If we assume speeds achievable with foreseeable near-term technology, perhaps 1 to 5% of light speed, the shell shrinks further, to perhaps a few 100 million galaxies or fewer. Inside the probe shell sits the region reachable by crewed vessels. This is smaller still. Crewed vessels are heavier, more complex, and more fragile than probes. Their practical speed limits are lower, their engineering challenges are steeper, and their probability of successful arrival at any given target is much lower. A generous estimate might place the crewed frontier at perhaps a few % of the probe frontier in volume. Though this is admittedly rough, inside the crewed shell sits the region of actual settlement, where a lasting human presence could be established and sustained. This is the innermost and smallest shell of them all, and estimating its size honestly requires enormous humility. Under optimistic assumptions about self-replicating probe technology, downstream settlement, and civilizational persistence across timescales dwarfing human history, the settlement frontier might encompass a few billion galaxies. Under more conservative assumptions, it might be much smaller, perhaps thousands or millions of galaxies rather than billions. Under pessimistic assumptions, where crude interstellar travel proves impractical and settlement remains confined to nearby stellar systems, the settlement frontier might be dramatically smaller still, perhaps limited to our own galaxy, the Milky Way, or the immediate neighborhood of the local group. Notice the enormous range of these estimates. This range reflects genuine uncertainty. We do not know how far we can push propulsion technology. We do not know how well biological beings can survive long-duration relativistic travel. We do not know how self-replicating probe technology would actually behave once we tried to build it. We do not know how durable a self-sustaining civilization can be across cosmic timescales. Every one of these questions has answers that could shift our estimates by orders of magnitude. We are not standing on solid ground when we quote a single number for humanity's settlement frontier. We are painting a range, and the range is wide. But two features of this picture are robust, and they matter enormously. The first is that every shell is much smaller than the shell outside it. Whatever your assumptions, the region humanity could visit is a tiny fraction of the region humanity could see. The region humanity could settle is a tiny fraction of the region humanity could visit. And even the most optimistic estimates of settlement leave us confined to a small subset of the causal universe, which is itself only 5% of the visible universe. The second is that all of this arithmetic depends on getting started. The delay penalty is real. It does not care whether we consider it fair. Every year we remain confined to Earth is a year during which the accessible region shrinks. Every century, every millennium, every million-year delay pushes territory beyond our effective reach. There is a genuine physical incentive to begin expanding sooner rather than later, and the incentive grows more urgent, in some sense, as the years pass. This is not a rhetorical flourish. It is a straightforward implication of the cosmological equations. The universe does not wait for anyone. Now, before we close this stage of our journey, we should acknowledge that everything we have discussed so far, from the causal frontier down through the settlement frontier, depends on our current best cosmological model being roughly correct in its predictions for the far future. We have assumed that dark energy behaves like a cosmological constant, that expansion continues to accelerate at approximately the current rate, and that the event horizon remains near 16 billion light-years of proper distance, essentially forever. These assumptions are consistent with the vast majority of current observations. They form the baseline of modern cosmology. They are what most textbooks and most working cosmologists would use if asked to sketch the future of the universe today. But they are assumptions. And the recent hints from DESI, along with other measurements, remind us that our understanding of dark energy is not yet complete. If dark energy is not perfectly constant, if it evolves in ways we do not yet understand, then the event horizon may not sit exactly where we have placed it. The reachable region may be larger or smaller than our current estimates suggest. The final frontier of humanity might be different, in ways that matter. That is the territory we will explore next, along with the deeper philosophical weight of the answers we have already reached. We have calculated, as best we can, how much of the cosmos humanity could ever affect, visit, and inhabit. We have found that the answer is simultaneously enormous and painfully constrained. Enormous by any standard of human experience, painfully constrained relative to what our telescopes reveal. Now we must ask what that answer means, how it depends on cosmology we are still refining, and what it says about our species' ultimate place in a universe that is mostly and permanently out of reach. We have arrived at the moment of reckoning. We have traced humanity's cosmic reach through 5 nested shells, from the 2 trillion galaxies we can see, through the roughly 100 billion galaxies we could ever affect, through the smaller region a probe could visit, through the smaller still region a crewed vessel could reach, down to the innermost region where a lasting settlement could be established. It is time to state the verdict clearly, and it is time to be honest about how much of that verdict depends on the cosmological model we have used to reach it. Let us begin by naming the verdict in one plain sentence. Under our current best cosmological model, humanity could eventually reach an enormous region of the universe containing more galaxies than any civilization could meaningfully explore, and yet that region is only a small sliver of everything visible, and the region we could actually settle is smaller still. The observable universe is not humanity's inheritance, it is our view. Our inheritance, whatever we choose to make of it, lies inside a much tighter frontier, and beyond that frontier lie galaxies whose ancient light we can gather, but whose futures we can never touch. Now let us break this verdict into its 3 tiers, cleanly, so we can hold each one in mind. The first tier is the absolute causal region. This is defined by the cosmological event horizon under the standard cosmological model, sitting at roughly 16 billion light-years of proper distance today. Inside this region live about 100 billion galaxies, roughly 5% of the visible universe. This is the region a light-speed signal launched now could ever influence. It is the maximum, the ceiling, the outermost line of humanity's possible causal footprint. No engine, no future breakthrough, no successor civilization could ever expand this region because it is set by the geometry of expanding spacetime itself. If humanity, or any beings descended from humanity, ever mattered to the futures of any of those 100 billion galaxies, it will be because a signal, a probe, or a mission launched from within the region containing Earth eventually arrived there. The second tier is the practical reach of physical spacecraft. Under generous assumptions about propulsion technology, perhaps achieving speeds of 10 to 50% of the speed of light for automated probes, this tier captures a substantial fraction of the causal region, though never the full 100 billion galaxies. A realistic estimate might place the practical probe frontier at somewhere between 1 billion and 50 billion galaxies, depending on how optimistic our assumptions are about propulsion, engineering, and probe autonomy. This is where the real physical activity of any expanding civilization would take place. Probes would be sent, targets would be studied, and the map of accessible galaxies would gradually be filled in over cosmic timescales measured in tens or hundreds of billions of years. The third tier is the region of actual lasting human settlement. This is where our estimates become most humble. If crewed interstellar travel proves possible in any meaningful form, and if self-replicating probe technology can eventually deliver the seeds of downstream civilization to distant galaxies, then the settlement frontier might encompass anywhere from a few million to a few billion galaxies. If crewed interstellar travel proves impractical, or if civilizational continuity across cosmic timescales proves too fragile to sustain, the settlement frontier might be dramatically smaller, perhaps limited to a modest number of galaxies in the neighborhood of the local group, or even confined to our own Milky Way. The range of honest answers spans many orders of magnitude, and we are not standing on solid ground when we quote any single number. We are painting a range, and the range is wide. That is the verdict, stated as clearly as our current understanding allows. Now we have to ask a harder question. How much of this depends on the cosmological model being right? The standard model of cosmology, which we have used throughout our journey, treats dark energy as a cosmological constant. It assumes that the mysterious component driving cosmic acceleration has the same value everywhere and at all times, and that its influence will continue to push the universe apart at an ever-increasing rate indefinitely. This assumption is not arbitrary. It is the simplest possible description of dark energy that fits the data, and for most of the nearly 30 years since the discovery of accelerating expansion in the late 1990s, it has provided an excellent match to essentially every major cosmological observation. The cosmic microwave background, the large-scale distribution of galaxies, the brightness of distant supernovae, the abundances of light elements produced in the early universe, all of these are consistent with a universe in which dark energy behaves as a constant and expansion continues to accelerate. But in the last several years, observations from the Dark Energy Spectroscopic Instrument, DESI, have hinted at something more subtle. When DESI's measurements of the large-scale distribution of galaxies are combined with other cosmological data, particularly measurements from the cosmic microwave background and from Type 1a supernovae, the combined analysis shows a mild preference for a dark energy that evolves over cosmic time rather than remaining constant. Specifically, the data hint at a form of dark energy that was somewhat stronger in the past and may be weakening today. We have to be very careful about how strong we make this claim. The DESI results announced in 2024 and 2025 reach statistical significance in the range of about 2 to nearly 4 standard deviations, depending on which combination of datasets is analysed and which parametric model of dark energy is assumed. In physics, and especially in cosmology, this level of significance is intriguing but not decisive. A 4 sigma result sounds impressive, and it is worth investigating carefully, but the history of cosmology contains many examples of interesting anomalies at this level of significance that later evaporated when better data arrived or when systematic effects were more carefully accounted for. The current situation with dark energy might be a real signal of new physics. It might be a statistical fluctuation. It might be an artifact of systematics not yet fully understood. The community is actively investigating, and further data from DESI, from Euclid, from the Vera Rubin Observatory, and from the Nancy Grace Roman Space Telescope over the coming years will help settle the question one way or the other. So, we cannot declare that dark energy is definitely evolving, but we also cannot declare that dark energy is definitely constant. The honest position is that the standard model remains our best working assumption, while a modest but genuine possibility exists that the model will need to be updated in the coming decade. And if it does need to be updated, the implications for humanity's cosmic reach are real. Let us walk through the 3 main scenarios, so we can see how sensitive our verdict is to what dark energy actually does over the coming cosmic ages. The first scenario is the standard model, in which dark energy is a true cosmological constant. This is the reference case. the event horizon remains near 16 billion light-years of proper distance, essentially forever. The reachable region is what we have described throughout this episode. Humanity's frontier is what our tiered verdict says it is. This is the picture almost every modern cosmology textbook presents as the default expectation. The second scenario is what happens if dark energy is weaker than the standard model assumes, or if it weakens over time. In this case, the acceleration of cosmic expansion slows, and the event horizon effectively moves outward. Objects that would have been permanently beyond reach under the standard model might, in this scenario, become reachable, because the expansion is not carrying them away as rapidly. In the most extreme version of this scenario, if dark energy weakens dramatically or eventually reverses sign, the event horizon could dissolve entirely, and the reachable region could grow to encompass essentially the entire observable universe, given enough cosmic time. This is not the mainstream expectation, and there is no strong evidence for it, but it is a possibility that some interpretations of the recent DESI results have raised, and it deserves to be named honestly. The third scenario is the reverse. If dark energy is stronger than the standard model assumes, or if it strengthens over time toward what physicists call phantom energy, then the acceleration of expansion increases more rapidly, and the event horizon shrinks. The reachable region contracts. Galaxies that would be reachable under the standard model become unreachable. In the most extreme version of this scenario, the strengthening dark energy eventually tears apart not just galaxy clusters, but individual galaxies, and ultimately individual stars and even atoms, in a scenario called the Big Rip. This too is not the mainstream expectation, but it is a mathematically possible outcome, and various current models of evolving dark energy admit trajectories that lean in this direction. It is worth trying to attach approximate numbers to these three scenarios, because the difference in humanity's reach across them is not small. Under the standard model, the event horizon sits at 16 billion light-years, and the causal region contains roughly 100 billion galaxies. If dark energy is weakening in the way the most optimistic interpretations of DESI hint at, the event horizon could grow. In some models, it might expand to 20 or 25 billion light-years within the next few tens of billions of years, potentially adding hundreds of billions of galaxies to the region humanity could ever affect. In the truly optimistic edge case where dark energy weakens dramatically or vanishes, the event horizon could dissolve entirely, and the causal region could eventually grow to encompass essentially the whole observable universe. In principle, this would mean that all 2 trillion visible galaxies could, given enough cosmic time, become part of the region a signal launched at some future date could reach. That would be an astonishing revision of our situation, and it deserves to be named as a live possibility rather than dismissed. But it is not currently supported by strong evidence, and it should not be treated as expected. On the pessimistic side, if dark energy strengthens toward phantom behavior, the event horizon shrinks. In moderate versions of this scenario, the reachable region contracts to perhaps 12 or 13 billion light-years, and the number of galaxies inside falls from around 100 billion to perhaps 50 or 60 billion. In severe versions, the event horizon could shrink toward the scale of nearby superclusters, cutting the affectable region by an order of magnitude or more. In the extreme Big Rip scenario, the effective horizon eventually collapses to subgalactic scales, and the very structure of the cosmos ends in a few tens of billions of years, taking any prospect of long-term civilization down with it. The honest position, given current data, is that the standard model is still our best guess, and the most likely outcome is that the boundary sits close to where we have placed it. But the range of scenarios consistent with observation spans roughly a factor of 10 in the size of the reachable region, and possibly more. Our verdict about humanity's cosmic future is a probability distribution, not a single number. The center of that distribution is what we have described. The tails include possibilities that are dramatically better or dramatically worse than the center. All of them share the same fundamental structure, a bounded region, much smaller than the visible universe, whose exact size we cannot yet pin down. The point of walking through these three scenarios is not to say that any of them is confirmed. It is to say that our verdict is conditional. If the standard model is correct, humanity's reachable region is what we have described. If dark energy is weaker than expected, the reachable region could be larger. possibly much larger. If dark energy is stronger than expected, the reachable region could be smaller, possibly much smaller. The final answer to how much of the universe humanity could ever affect is not written in stone. It depends on physics we are still refining, and the answer might, in the coming decade or two, shift in ways we cannot currently predict. That said, we should not overstate the uncertainty. Under the vast majority of viable cosmological scenarios consistent with current data, the reachable region falls somewhere between a substantial expansion of the Standard Model estimate and a modest contraction of it. The overall picture, humanity able to reach an enormous but bounded region containing far fewer galaxies than the observable universe, is robust across the range of plausible scenarios. What changes is the exact size of the boundary and the exact number of galaxies inside it. What does not change is the fundamental structure of the answer. Humanity's cosmic domain, whatever its precise size, is much smaller than what humanity can see. Now we come to the deeper question. What does all of this mean? There is a temptation, when confronted with these numbers, to slide into one of two easy responses. The first is dismissive nihilism. Humanity is so small compared to the universe, this response says, that our existence is meaningless. Nothing we do matters at cosmic scales. Our concerns are laughably parochial. This response has a certain grim appeal, but it is philosophically confused. The size of the universe, and our small place within it, does not by itself imply anything about the meaning or value of what we do. Meaning is not measured in cubic light years. A human life, a human civilization, a human future has whatever significance it has because of what it is, not because of how many galaxies it could theoretically influence. The vastness of the unreachable universe is a fact about geometry. It is not a verdict on human worth. The second easy response is overreach in the other direction. Humanity's future is limitless, this response says. If we could reach 100 billion galaxies, that number is so large that it might as well be infinite. Any concern about the 95% of the observable universe we cannot reach is a rounding error. This response is also confused, in the opposite way. 100 billion galaxies is not infinite. It is a specific bounded number, and it represents a specific bounded fraction of what exists. If we treat that number as effectively infinite, we obscure the genuine structure of our cosmic situation. We lose sight of the fact that our reach, however enormous by human standards, is finite and defined. The honest response, the response that does justice to what we have learned, is neither of these. It is a recognition that humanity's potential cosmic domain is simultaneously enormous beyond any capacity for meaningful imagination, and yet bounded by an absolute horizon that no achievement could ever cross. Let us take a moment to feel the enormousness first, because it deserves its due. 100 billion galaxies is not a number the human mind can properly hold. If we imagine dedicating a single second of attention to each galaxy inside the causal region, uninterrupted, we would spend more than 3,000 years counting them. And each of those galaxies contains, on average, hundreds of billions of stars, most of which likely host planets, and some fraction of those planets likely offer conditions where life could arise. Even if only a vanishingly small fraction of galaxies inside the causal region ever come to host settled outposts of human descendants, the sheer number of possible destinations, possible histories, and possible futures inside that region is beyond anything our species has ever contemplated. A civilization that spread across even 1,000th of 1% of the causal region would inhabit more stars than there have ever been human beings, by a factor of trillions. The scale of what could, in principle, be ours is not small. It is inconceivably, extravagantly, incomprehensibly large. And yet, it is not everything. It is not even most of what we can see. 95% of the 2 trillion galaxies visible to our telescopes lie beyond the causal region. And we have to be very clear about what this means. Those galaxies are not merely far away. They are not merely hard to reach. They are permanently, structurally, geometrically severed from our future. Their light still arrives at our detectors, carrying information about their past, but their present, if that word even means anything across such distances, is a place we can study and never influence. Their futures are their own. Nothing we ever do, no matter how great our technology, no matter how patient our civilization, no matter how far into the future we look, will affect them. The very shape of space-time forbids it. This is a strange kind of loss. It is not the loss of something we ever had. It is the loss of something we can see but never touch. A cosmic version, perhaps, of watching a photograph of a person we can never meet. Those 1.5 trillion unreachable galaxies are, in a sense, memorials. They are messages arriving from places already past every possible journey, and they will continue to arrive for as long as the universe permits, patiently delivering light that carries information we can study but no meaning we can add to. There is a further strangeness worth naming here, and it concerns what the sky itself will look like far into the future. Under the standard cosmological model, the accelerating expansion of the universe means that distant galaxies are not just permanently beyond our reach. They are, over time, redshifting themselves out of visibility altogether. Every year, the light arriving from the most distant galaxies stretches to slightly longer wavelengths, growing dimmer and cooler and harder to detect. In tens of billions of years, essentially every galaxy outside our own local group will have redshifted so far into the infrared and beyond that it will become undetectable to any conceivable telescope. The 2 trillion galaxies visible to Webb and its successors today will, in the distant cosmic future, quietly fade one by one from the observable sky. Imagine an observer living in the merged Milky Way Andromeda galaxy roughly 100 billion years from now. They look up at their night sky and they see stars. They see their own galaxy stretched around them, transformed by the merger and the passage of time. But they see essentially nothing else. No Virgo cluster, no Coma cluster, no distant spirals, no deep field images filled with 100,000 faint smudges of ancient light. The rest of the universe has quietly slipped past the observable horizon and vanished from view. If that observer never learned the history of cosmology, they might reasonably conclude that their galaxy was the entire universe, a single island of stars floating in an infinite void of nothing. We are, in an important sense, extraordinarily lucky to be alive at this particular moment in cosmic time. We can still see the 2 trillion galaxies. We can still gather evidence for the expansion of the universe, for the acceleration driven by dark energy, for the microwave background left over from the Big Bang. We can still piece together the history of the cosmos, because the evidence is still arriving at Earth and still detectable. A civilization arising much later would not have this privilege. Its cosmology would be strictly local, and the vast structure of the universe beyond the local group would be, for that civilization, essentially undiscoverable. This is not a small point. It changes what it means to reach the frontiers we have been describing. The window during which any civilization could even know the shape of the challenge is itself finite. We happen to be inside that window. Those who come far after us will inherit a smaller, quieter, more isolated cosmos, and their sense of humanity's possible reach will be, of necessity, more modest than ours. There is a related observation about what it means to launch missions that outlast any possible reply. A civilization that sends a probe to a galaxy 10 billion light-years away is at the moment of launch committing to an act of pure hope. Nobody launching the probe will ever hear back from it. Nobody at the destination, if the probe arrives, will ever be able to communicate meaningfully with Earth. The very civilization that funded and built and launched the mission will almost certainly no longer exist by the time the probe reaches its target, tens or hundreds of billions of years later. What kind of act is that? It is not exploration in the ordinary sense, because exploration implies bringing knowledge back. It is not colonization in the ordinary sense, because colonization implies remaining connected to the parent civilization. It is something stranger, something closer to a gift launched into the darkness, an act performed for the benefit of a future so distant that its beneficiaries cannot even be imagined. To do this at cosmic scale would be to accept, at the deepest level, that the future of our species is not something we participate in. It is something we contribute to and then release. There is one more piece of this picture that deserves to be named clearly. Under the standard cosmological model, as time passes, the situation gets slowly worse. The event horizon effectively shrinks in the co-moving frame, and galaxies that are currently just inside the causal region will, in the distant cosmic future, slide out of it. This does not affect the ancient light that has already arrived, but it does affect the reachability of those galaxies for anything launched at that later time. 100 billion years from now, if some successor civilization descended from humanity were to attempt to launch new missions to what is currently the outer edge of our causal region, they would find that many of those targets had already passed beyond effective reach. The window of opportunity is enormous in absolute terms, but it is not infinite. The universe does not wait. This is not, however, a reason for existential panic. The timescales involved are vast beyond anything that could reasonably guide our current decisions. 1 million years of delay costs relatively little at the edges of the frontier. 1 billion years costs more. 10 billion years starts to matter significantly. And on the human timescales that actually apply to us, the frontier shrinks at rates that are, for practical purposes, imperceptible. There is no immediate cosmological deadline. What there is, instead, is a general principle. The frontier is finite. It responds to when we act. And the sooner any expanding civilization begins, the more territory remains available to it. Now let us return to a philosophical thread we have been holding at bay throughout this journey, and let us give it the attention it deserves. What does it mean to be a species whose potential domain is so large and yet so bounded? There is something quietly extraordinary about the position we occupy. We are beings on a single planet, orbiting a modest star, in an ordinary galaxy, in a universe we have only recently begun to understand. A century ago, our species did not know that other galaxies existed. 90 years ago, we did not know the universe was expanding. 30 years ago, we did not know that expansion was accelerating. Only a few years ago, we could not yet gather deep field images of galaxies from the earliest epochs of cosmic time with the clarity that the James Webb Space Telescope now provides routinely. We are the first generation of humans to have any real answer to the question we have been exploring in this journey. And even our answer is provisional, subject to revision, as we learn more about the fundamental nature of the cosmos. That we can pose the question at all is a remarkable fact about our species. That we can answer it, even provisionally, is more remarkable still. We are creatures shaped by evolution for the challenges of a small savannah, whose brains, in principle, have no business grappling with the geometry of expanding space-time, the behavior of dark energy, or the future reach of light-speed signals across 100 billion years of cosmic time. And yet, we do grapple with these things. We compute them, we refine them, and we allow them to shape our sense of what we are. The answer we have found is, in one sense, humbling. Most of the visible universe is not for us. The overwhelming majority of what our telescopes reveal is scenery, not territory. This is a fact about the cosmos, not a judgment about us. It is not a failure of engineering, a failure of ambition, or a failure of imagination. It is a consequence of the shape of space-time, and no amount of any of those human virtues could ever alter it. But in another sense, the answer is expansive beyond anything our species has ever considered. The region we could, in principle, affect contains 100 billion galaxies. The region we could, under generous assumptions, actually visit contains many billions of galaxies. Even the region we could realistically settle, on the most conservative honest estimates, contains a number of star systems that exceeds every human life that has ever been lived by many orders of magnitude. Our potential domain is not small, it is unimaginably large. It is just not everything. Perhaps that is the truest way to state the verdict. One final time. Humanity's ultimate frontier is not set by the quality of our engines. Better engines would let us reach more of what physics permits. Longer-lived civilizations would give us more time to fill the accessible region. Cleverer probes would extend our practical reach toward the theoretical maximum. All of these achievements would matter. All of them would enlarge what our species could become. But none of them could ever cross the final line. Beyond the event horizon, whatever its precise location turns out to be, lie galaxies whose ancient light we can gather and study, but whose futures we can never join. They are not obstacles to be overcome by future technology. They are, in the deepest sense, elsewhere. Their existence is real, their light is real, their histories are real, and yet they are separated from us by a barrier no achievement could ever breach. The final image, then, is this. Imagine humanity, or its descendants, spreading across cosmic time. Imagine the expansion front sweeping outward from Earth at some fraction of the speed of light, seeding galaxy after galaxy with outposts, machines, habitats, and eventually settled societies. Imagine this process continuing for tens or hundreds of billions of years until the reachable region is at last fully mapped, fully touched, and in some parts fully inhabited. Imagine, if you like, that this future is achieved in its most optimistic form, and that humanity's descendants come to occupy every galaxy that any signal launched from Earth today could ever reach. Even then, 95% of the visible universe remains outside. From the perspective of humanity's furthest outpost, on the last galaxy just inside the causal region, the telescopes there would still see trillions of galaxies stretching outward in every direction. Their light would still arrive, their ancient histories would still be readable, and all of them would still be, forever, beyond every possible journey, places we could see and places whose futures could never contain us. That is what it means to live inside an expanding cosmos with a cosmological event horizon. That is the cage, and it is also the invitation. The cage tells us where our futures can never go. The invitation tells us how enormous, how varied, and how unbounded by any human standard our possible territory truly is. The question is not whether we could, in principle, reach everything. We cannot. The question is, what we would choose to do inside the enormous region that remains available to us, and whether we would begin soon enough to make the most of the frontier we still have. The universe is not our inheritance. It is our neighborhood, our library, and our horizon. Only a piece of it could ever be our home, but that piece, in every honest accounting, is larger than any story we have ever told about ourselves, and it is waiting for whatever we decide to become.